Hey everyone, my name is Aniruth, and today we're going to be going through question 4 from quiz 2 of CS61BL. I'm going to be going through my thought process as I think about these questions in the hopes that it helps you think about how to approach these questions and maybe some things that you can think about when you're approaching these questions on your own. So this very first question is asking about a program Boolean is prime, which is designed to determine if a number is prime. Gives us the definition, gives us a couple assumptions, okay. And now we are asked to determine which of the following Boolean conditions is true for any number of 1 is less than x is less than n. So basically x is between 1 and n if the number n is prime. Okay, so it's interesting that x is between 1 and n and that x is not actually 1 or n. And I think that the reason why is because when we think about the definition of a prime number, we don't need to check if a number is divisible by 1 or by itself because the answer is going to be yes. And that does not give us any information about whether or not something is a prime number. We just need to check every other number in between those. So as an example, let's say I was to have the number 6. So if I'm to draw a little text box and I check 6. Well, 6 is not a prime number because 6 is divisible by 2. And I can write this as 6 mod 2 is equal to 0. Or in fact, 6 mod 3 is equal to 0. And the issue with this is that, well, 2 and 3 could be x's, right? It should be true for any number. And since 2 and 3 are both numbers between 1 and 6, it means that this number 6 cannot be prime. But if I had 7 on the other hand, well, I can check it against 1, actually not 1, right? Because x has to be greater than 1. I can check it against 2, 3, 4, 5, or 6. And in every single one of these cases, they're all going to come out to 7 mod this number is not going to be equal to 0. So I can write out 7 mod x is not going to be equal to 0. And I guess you can sort of see where I'm going with this, which is that I'm going to go ahead and select the third option, n mod x is not equal to 0, because it follows from that definition, right? If you think about what the definition means, it means that I should be able to check this number against every single others and make sure that none of those numbers divide n. If any of them do, that would mean that n mod x is equal to 0, and that means that it's not a prime number. So this is a condition that has to be true, and we can keep this in mind for the next question. So I'm looking at this question, and it says we want to now implement this. It could be inefficient, but it needs to be accurate. Okay, so it needs to be right. At least one of the below is correct, and we need to select the letter corresponding to the correct answer. Okay, so I'm going to go ahead and write the condition that we had before. And that condition is n mod x is not equal to 0. And then if I take the not condition, that's going to be, well, n mod x is equal to 0. So this will just be useful when we approach these questions below. So let's take a look. I'm going to turn on the laser pointer. We have 4 options here. Let's go through all 3. So A, there's something that pops out to me, which is that we're using a while loop, but in the others, we're using a for loop. Okay. Well, we started with int x is equal to 2. Then we while x is less than n. We check the condition, and if the not condition is true. So if n mod x is equal to 0, we return false, right? And this makes sense. If we have a number where, like, for example, 6 mod 2 is equal to 0, it satisfies the not condition, then we do want to return false. Otherwise, we want to return true if we go through every single loop. The problem, though, is that this is missing one line, and that line that it's missing is x plus plus, right? We want to increment x every single time. Otherwise, we just keep going around in a circle over and over and over and over, because it means that we never break out if n is greater than 2. For example, if you try it with 3, you're going to get 2 is less than 3. You're going to check the condition. You're going to say 3 mod 2 is not equal to 0. So then you don't enter the if statement. You don't return anything. But then you check the same while loop again, which is going to be true again, so on and so forth, because you aren't changing anything about what determines the while loop. So we can cross out A because this is clearly not an accurate implementation of the method. Now we go to B. So B is effectively A, but the only difference is now we have the increment. So B looks to be right because everything else about A made sense except for the fact that it was an infinite loop. So I'm going to go ahead and circle B. I'm going to circle B a little bit cautiously. Maybe it turns out that we thought about this wrong, and we'll look at the other answers. Take a look at C. So we have for int x equals 2, x is less than n, x plus plus. Okay. So it's interesting. Now we have a flip. We have if condition return true, otherwise return false. And personally for me, I would take the time to write out a quick example, right? Just a handful of prime numbers. If you look at the prime numbers between 1 and 10, or you just check every single one of those, right? You check 2, 3, 4, 5, 6, 7, 8. Or maybe you don't need to check that many. Maybe you'll notice the pattern before then. But if you check a handful of numbers, hopefully you'll see a little bit of a pattern. But let's see why that pattern exists. So if I take a number, for example, let's say I take the number 9. And I'm picking 9 very deliberately, and there's a particular reason why, which is that if I do if condition, and x starts out as being 2, right, from the initialization. So if 9 mod x is not equal to 0, that is true, right? 9 is an odd number. Then we return true. The problem is 9 is not a prime number, right? Because we never checked 3. So just because it satisfies the 2 does not mean that it satisfies the 3, does not mean it satisfies the 4, does not, etc. So if I'm to think about this, it's a condition that satisfies any number. Well, let me underline instead, right? It's true for any number, not just a number that you can just pick and choose, which means that this condition is false, not the condition, the C is incorrect because it means that we're just really checking if a number is odd or not. And if it's not odd, if it's even, then we keep cycling through and then we can return false maybe. But anyway, the more important part is that this does not work, right? Because we need to be checking all the numbers, and just because you're not divisible by 2 does not mean that you are prime, which means that you cannot return true. And now finally we check D, and D looks to be very similar to B. The difference is we have an else. And that's going to be a little bit of a problem because it means that whenever we check something, we're going to be returning on the first iteration. So in other words, we never actually get to this. This may as well not exist because we're checking the condition or the not condition, which is, as we wrote up here, n mod x is equal to 0. And if that's true, we return true. Else we return false. But when did we ever check 3? So if I put 9 here, what's happening? I check if not condition. So not condition is n mod x is equal to 0. So n9 mod 2 is not equal to 0, right? We covered 9 mod 2 is 1. But the issue is now we immediately go to the else and we return false. Okay, so maybe 9 works. But let's check a different number, right? Let's say we pick the number, let's say we pick the number 4. So now I check the same not condition. Is 4 as n mod 2, is that equal to 0? Well, it is equal to 0. But the issue is now we're returning true. So there's a couple of different ways that you can think about this one, right? As to why D doesn't work. The one that I like to think about is that since we have an if else, we're going to be returning a value after the first iteration, which means that we only check for x is 2 and that we're not checking for any of the other numbers, which means that it has to be wrong. Or you can try with an example like how I did here. I chose the number 9 because it seems like a nice square number that's divisible by 3. But if I'm to pick another one like 4, then I can pretty clearly tell that D doesn't work either. So I know that the correct answer here is B and B alone. Now we come down to part 2. So now we're trying to make it a little bit more efficient. And the way that we make it more efficient is we consider fewer x's. So now we change the loop's stopping condition. We need to check which of the following are correct. Okay, again, so that means that there could be multiple answers, and which would make the code more efficient. And it's a hint, and this hint is going to be really, really important. So I'm going to go ahead and underline it because that's how important it is. Actually, I'm just going to underline this last part, square root of n, which is that you only need to check the factors until the square root of n. So we're given this, and I'll talk about why this is true after we finish this, but let's say that I know this is true. Now the question is, which of these three is that? So if I take n to be the number 9, I'm picking 9 here because it's a square number, so the square root of 9 is 3. So I only need to check the factors until the square root of n. So I need to check 2. Again, I'm not checking 1 because, like we said, 1 is less than x is less than n. Every number is going to be divisible by 1. But I need to check 2 and I need to check 3. Right? Of course, we need to check 3 because we know that 9 is not actually prime. But we don't need to check 4. We don't need to check 5. We don't need to check 6. We don't need to check 7. We don't need to check 8. So we only need to check 2 and 3. And as you can see, we're checking literally a quarter of how much we would have checked otherwise. But now the question is, which of these satisfies this case? And in this particular case, because we have options provided to us, we can just plug it in. If we have x is less than or equal to n times n, well, n times n is 81. Well, then we're checking from 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., all the way up to 81, which is definitely not what this is saying. Then we have x star x, or x times x, is less than or equal to n. This one looks to be a little bit more plausible because if I have 2 times 2, I know that's less than n, so I can try 2. If I have 3 times 3, I know that's less than or equal to 9, right? It is 9. But if I have 4 times 4, 16 is greater than 9, which doesn't satisfy. So I think that this part is right. And in fact, I can actually simplify this, right? If I do x squared is less than or equal to n, and then I can rewrite this as x is less than or equal to the square root of n. And I can do this because we're dealing with all positive numbers here. I believe that was mentioned up here. Assume that n is a positive number. And again, we're checking x between 1 and n, which means that they're both positive, so we can take the square root. So this pretty clearly seems to be the right answer. And if we take a look at the third option, that was x cubed is less than or equal to n, which only checks to the cube root of n, not actually to the square root. So that is